Hello, my name is Julio Sebastian, and today I will be talking about one of the world's most popular drugs, caffeine. To begin, I would like to share my outline of my presentation. So, first, I'll be talking about the discovery of caffeine, and then sources of caffeine, and then caffeine itself, structure, and effects, and then I'll talk about the mechanism of action of caffeine. Then I will talk about the structure and effects of adenosine, then compare adenosine with caffeine, and then show how adenosine and caffeine interact with the adenosine receptors, and then talk about the metabolism of caffeine, and then I will conclude with my presentation. So, the discovery of caffeine. The caffeine was isolated in 1819 by Friedrich Ferdinand Runge, and this was a discovery that was a result of an encounter between Runge and Johann Wolfgang von Goethe. So at that time, Van Gogh was a very famous poet, actually one of the most well-known poets at that time, and Runge was just a young physician slash chemist. Runge studied under Dr. J.W. Dobereiner, and Dr. J.W. Dobereiner was also an advisor to Van Gogh, so there was Runge's first connection to Van Gogh. And as a young physician, one day Runge was preparing a medicine using extracts from the nightshade plant, and when he was extracting the juice from the plant, he accidentally splashed a drop of the extract into his eyes, and a few minutes later he noticed that his eyes dilated when he looked in the mirror. And so this is a finding that was, even though it was accidental, it led to something good. So Runge redid the experiment on his cat, and he noticed the same result, that the pupils dilated. So Runge told Dr. Dobereiner about his findings, and Dr. Dobereiner arranged a meeting for Runge to demonstrate this procedure in front of Van Gogh. So Runge goes and demonstrates this procedure, and Van Gogh was very impressed by this procedure. So in exchange, he gave Runge a gift, and this gift was a box of rare Arabian mocha coffee beans. And he, even though it was a gift for Runge, Van Gogh gave it to him with the intention for Runge to perform an analysis on the coffee beans and to report to Van Gogh his findings, because Van Gogh was curious as to why, when he drank this coffee, he felt more awake, focused, and alert, and when he didn't drink the coffee, he just felt normal, and then throughout the day he felt more tired. So the discovery of caffeine was because of an encounter between Runge and Van Gogh. So caffeine is a natural stimulant for the nervous system and the body, and it can be extracted from over 60 different plant species, but these three are the most common that we know of. So these are cocoa beans, and these right here are coffee beans, and these are tea leaves. Now, cocoa beans can be used to make chocolate. That, I hope everybody likes chocolate. And coffee beans can be used to make coffee, which we probably drink at least once a day. And tea leaves, which are used to make tea. Now, even though caffeine can be obtained naturally, it can also be obtained synthetically. There are many ways to obtain caffeine synthetically, but this is just one of them. So you start out with uric acid, and then you add sodium hydroxide and methyl iodide into a solution, and these reactants, sodium hydroxide and methyl iodide, will methylate the in here, here, and here, and it will give us the 1,3,7-trimethyluric acid product. And then once we get this product, we add phosphorus pentachloride into the solution, and then this oxygen gets replaced with a chlorine, or it gets chlorinated, and we get chlorocaffeine from 1,3,7-trimethyluric acid. And then once we have chlorocaffeine, we add hydrogen iodide, and then this chlorine gets eliminated, and we're left with caffeine. Now, synthetic caffeine and natural caffeine have the same chemical structure. There's really no difference. The only difference is that natural caffeine is obtained naturally, and synthetic caffeine is made. So now that we talked about how to make synthetic caffeine and natural caffeine, this is the structure of caffeine right here. And then this is just a ball and socket model of the same structure that is seen right here. The molecular formula is C8H10N4O2. And caffeine serves as a central nervous system stimulant, like I said earlier, but it also is an agonist. It's also an antagonist to the adenosine receptors found in our body. And this just means that an antagonist means that it prevents something from carrying out its job. In this case, caffeine prevents adenosine receptors from carrying out their job, which is to promote the body to enter rest or sleep mode. So now that I talked about structure of caffeine, I just want to give an overall mechanism of action of caffeine, but I will go more in depth into these later. But I just wanted to give an overall review real quick. So normally, let's see, for example, like myself, I am a student athlete, and throughout the day, on a normal day, I would go to class in the mornings, and then after class in the morning, I would usually go to the gym, and then right after the gym, I would have soccer practice, and this would really make me tired. So I would use a lot of energy throughout the day, and adenosine is a byproduct of energy consumption. So throughout the day, I do all these events, I guess I would say, and adenosine builds up. Now adenosine will start binding to adenosine receptors to promote adenosine receptors to tell the body to enter sleep rest mode. So that's why throughout the day, as you do more and more activities, you feel more tired because you have more adenosine built up in your system. But if you wanted to stay awake or a little bit more awake longer, you might drink a cup of coffee, or who knows, but usually people drink coffee. So I'll drink coffee, and then about an hour into drinking the coffee, some of the caffeine will be absorbed by in the small intestine, and caffeine will then start binding to adenosine receptors, but only a few. So you kind of start feeling a little bit more awake, but not really. But then after about 2 hours, which is the time it takes for the peak concentration of caffeine to be reached, then most of the adenosine receptors will be taken over by caffeine instead of adenosine. So this is the time where you're more like alert, you're more awake, because all your adenosine receptors are bound to caffeine instead of adenosine. But then, like all good things we know of, it doesn't last forever. So eventually, caffeine will start to unbind from the adenosine receptors, and the unbound caffeine will be transported to the liver to be metabolized. And then once it is metabolized in the liver, adenosine will basically take over the adenosine receptors again, and then you will start to feel tired again. So now that I've talked about how caffeine works, now I gotta talk to you about how adenosine works. But first, let's look into the structure of adenosine. This is the structure of adenosine. The molecular formula is C10H13N5O4, and here's a ball and stick figure. Now, as I said earlier, since caffeine is an antagonist to adenosine receptors, adenosine is an agonist to adenosine receptors, which just means that adenosine promotes adenosine receptors to carry out their function, which is to tell the body to enter sleep or rest mode. Now, here's a comparison between adenosine structure and caffeine structure. And the main takeaway from this is that caffeine and adenosine share this common xanthine moiety right here. And this will be an important aspect of both molecules later on. So now that I recently talked to you about this whole event or process, now we'll take them apart step by step. So right now I'm just going to focus on the adenosine receptors for the next few slides. And this is a amino acid sequence of the adenosine receptor, as it can be seen here. And the adenosine receptors are G protein coupled receptors, and all of the GPCRs are a 7-domain transmembrane protein. And these transmembrane portions can be seen right here. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and this is 7. So those are the 7 transmembrane domains of the amino acid sequence of the adenosine receptor. And here's the overall structure of the adenosine receptors. As you can see here, the 7 domains can be seen here again, each colored for a different transmembrane domain. So you can see 7 of them, 1 here, 1 here, 1 here, 1 here, 1 here, 1 here. So there's 7 right there. And since the adenosine receptors, when taken out of the membrane, are very unstable, they have to be stabilized by some stabilizing residues, which can be seen here and here. Now these residues don't have a function for the adenosine receptor. They're just there to stabilize it for the image, but then in the actual adenosine receptors, they're not present at all. So now that we've talked about the adenosine receptors, now we'll talk about how adenosine binds to adenosine receptors. So a refresher for the caffeine and adenosine structures. This is adenosine and this is caffeine. Now, this numbering system here is just for reference when talking about how adenosine and caffeine bind to adenosine receptors. This is not actually how they are numbered. Now, this is a picture of adenosine binding to adenosine receptors. So, the xanthine moiety of the adenosine, which can be seen right here, it establishes van der Waals interactions with M177, M270, I274, and pi stacking with F168 residues of the adenosine receptors. Now, the ribose moiety, which is not present in caffeine, establishes van der Waals interactions with valine 84 or L85, T88, W246, and L249 of the adenosine receptors, and then the carbon 2 and carbon 3 of the ribose moiety establishes hydrogen bonds with S277 and H278 of the adenosine receptors. This is probably the clearest image I could find about how adenosine binds with adenosine receptors. But one important thing to take away from this is that all agonists, including adenosine, bind to the helix 3 and helix 7 of the adenosine receptor at the same time. And so it binds helix 3 through T88 and helix 7 through S277 and H278. Now, one important thing here is that it binds to both of them at the same time, and this is important, and we'll see why in the next few slides. So now we've talked about how adenosine binds to adenosine receptors. Now we'll talk about how caffeine binds to the adenosine receptors. So here's when you drink your coffee, and then it slowly starts to compete with adenosine for adenosine receptors. And now here's when we are at peak concentrations right here. Now this is a picture of the adenosine receptor in complex with caffeine. So the xanthine moiety of caffeine produces the same interactions with the adenosine receptors as adenosine does. So that's the same. Now, one difference is that there's a water-mediated interaction between H278 of the adenosine receptors and the oxygen 11 of caffeine. Now, the biggest difference is that for some antagonists, including caffeine, they bind to either the helix 3 or helix 7 of adenosine, but never both at the same time. And this is important because this may suggest why adenosine this may be why adenosine promotes adenosine receptors to carry out their activity, and why caffeine, even though it binds, it doesn't promote adenosine receptor activity. Now that we talked about how caffeine binds to adenosine receptors, we can look at how, after we reach the peak concentration of caffeine concentrations, now it will slowly start unbinding and being metabolized. And in the end, we will have almost no caffeine concentrations in our body, and adenosine will take over again. So, caffeine is, like I said earlier, it's transported to the liver to be metabolized. Now, caffeine is metabolized by the CYP1A2 enzyme, and this enzyme metabolizes about 95% of caffeine. The other 5%, I'm not sure how it's metabolized. Couldn't find it in the reading, but yeah, 95% of caffeine is metabolized by CYP1A2. Now, caffeine is metabolized at 4 different sites, and these can be seen at the different colored atoms. So here, and here. Now, since they're metabolized at 4 different positions, we're gonna get 4 main metabolites of caffeine. So the first, those are theobromine, theophylline, paraxanthine, and 1,3,7-trimethyluritic acid. Now, the exact binding mode of how CYP1A2 binds to caffeine is not known, but the metabolites are known. So this is as much information as I can give about the metabolism of caffeine, because it's not known how it actually metabolizes. They just know that it metabolizes into these four main metabolites. Now, to recap about this whole process, I know this is probably, you're getting bored of it, but we're almost done. So, to recap again, after a long day of school, working out, soccer practice, adenosine builds up in my body and I start to feel tired. When I go to the cafe, eat dinner, I drink maybe 1 or 2 cups of coffee, and then about an hour later I can start feeling a little bit more awake, and then after about 2 hours, then that's when I feel most awake, so that I can do a little bit more studying and hopefully pass the class that I'm studying for. And so, like all good things, it doesn't last forever, and after a few more hours, then it will start unbinding from caffeine will start unbinding from adenosine receptors, and then it will be transported into the liver to be metabolized. And then after it gets metabolized, then adenosine will start to take over again, and that's when you'll start to feel sleepy again, and eventually fall asleep and wake up the next day, and same process again. So in conclusion, I went over the discovery of caffeine, then went over natural and synthetic caffeine, then went over the structure of caffeine, and then went over the main mechanism of action of caffeine, and then compared adenosine with caffeine, the structures, how they're similar, how they're different. And then I talked about adenosine receptors and how they interact with adenosine and caffeine. And then I went over the metabolism of caffeine. And that's it. And here's a list of my references. Thank you for bearing with me with this presentation. I hope everyone is doing okay, and hope for the best, and have a good day.